The next concept that we'll look at is that of SensorFusion. And in SensorFusion, what we're dealing with is combining sensory data from different sensors to result in better information than what we'd have from each of these sensors individually. And basically the idea is that a single sensor only gives us a partial amount of information about the environment. It doesn't tell us everything that there is to know. And even with our human body or anything else, we know that if we only had our eyes, well, we wouldn't be able to taste things, we wouldn't be able to hear things, we wouldn't be able to feel things. There's all sorts of things about our environment that we just would not know if we only had our eyes, or our ears, or any other sense for that matter. So here in SensorFusion, we want to combine this sensory data somehow and maybe get extra information from it, or understand what the environment is better than if we just use one of these sensors. Now, a few things to know about data that we obtain from sensors. It's always uncertain. So how do we know if we can trust the data? There's always a level of uncertainty and error associated with any data. It's also usually partial. It doesn't give us the full view and tell us everything about the environment. Occasionally it will be spurious or incorrect. So sometimes we'll have noise in our data. Sometimes there'll be specific errors, like reflections that we can have with some of our ultrasonic sensors and things like that. Sometimes there'll be noise, and the issue can be, in some circumstances, working out what's signal and what's noise. And often it's incomparable directly to other sensors for the reason that it's very difficult to physically put the sensors in exactly the same location and measure from exactly the same position, because they take up their own physical space. So each of these sensors won't have exactly the same view of the world. But no sensors are perfect. So sensors have different ranges, different operating constraints, different measuring techniques. They measure over different areas, have different resolutions. The sensor might be faulty, it might be temporarily faulty. They have flaws. For example, the deflection using ultrasonic sensors, flaws about, for example, our laser range finds that they need to actually reflect light. If it doesn't reflect light, well, then we're finished. And some of these sensors will be noisy at certain frequencies and not noisy at other frequencies. So when we're trying to design a robust system, we're trying to combine the best aspects from sensors and try and shield against the worst aspects from these sensors and try and rule those sort of ones out. So when we're talking about the concept of SensorFusion, we've got a number of sensors, and we have some sort of a perception from each of those sensors. We feed that into some sort of a fusion module, and we have a fused perception of the world, a fused perception of the environment. And then we can have some sort of behavior or decisions made and action that results from that. So there's a number of different types of sensor fusion. Our first one is using what we call redundant or competitive sensors, where we have essentially the same perception of the environment and generally the same types of sensors. We'll be talking about each of these in detail. We then have complementary sensors. In complementary sensors, we provide different types of information about the environment, normally from different types of sensors. And then we have cooperative sensors, where we're making these sensors work in sequence to gather information about the environment. Typically, the same type of sensors, but we're trying to get extra information from the environment, not just trying to improve reliability, but provide some sort of extra information about the environment. And we'll look at examples of each of these. So our first type of sensors, our redundant or competitive sensors, are primarily looking at trying to improve our accuracy. And this is what we have over on the far left, where we're looking at object A through two different sensors. These sensors happen to be the same sensors, and we're having some competitive fusion happening. In case one of these sensors is faulty or isn't working or something like that, the other sensor should be able to give us a correct reading. We might have 3 or 4 or more sensors and do some voting or something here to determine if one of these sensors is faulty or not working. It depends on the level of accuracy and reliability that we require. So this is our competitive fusion or redundancy. Our next one is our complementary fusion, where we're looking to increase our completeness of what we understand about the environment. Here we have two different types of sensors. And these two different types of sensors will give us two different understandings of the environment. For example, we might use an ultrasonic sensor and a laser rangefinder. And the laser rangefinder will give us great results and very, very accurate results, and even good results when we're coming up to acute angles where the ultrasonic sensor would bounce off. But it won't perform particularly well on surfaces that are non-reflective or surfaces that are see-through. Our ultrasonic sensor will. Our final one's our cooperative one, where we have the same sensors, but we get some emerging views. And the most common one, the most clear example of this is where we're using stereo vision, where we're using two cameras that are set apart by a baseline distance, and we can measure depth in the environment based on this. So we should mention that this concept of sensor fusion isn't just robot related, we have them as well. In our human body, one example we see of competitive sensor fusion is with our pain receptors. Basically, we've got a hollow pain receptors on our skin or just near our skin, and the more pain that we actually experience and the wider area of that pain we experience, we have more of these pain receptors firing and telling us that we've got a sore spot. Essentially, we've got a whole lot of receptors, and the sensor fusion is happening in a competitive sense, telling us what's happening over a wider area. We also have complementary fusion. So when we're measuring taste or flavour, it doesn't just rely on our taste buds. It's based on taste buds plus our smell, plus the texture of the food, plus the temperature of the food. If you try and eat some food when you're feeling sick and your nose is all blocked up and things like that, you know it tastes a bit different and tastes not normal. That's because some of these other things, for example, we can't smell the food, our flavour relies on that to give us a good sense of smell. And you can do tests where you eat some food and put a peg over your nose or something like that, and it becomes a whole lot more difficult to work out what that food is when that sense of smell is cut off. And a few places that we see cooperative sensor fusion is we've got two eyes, and those two eyes give us stereo vision, and we can determine depth from the disparity between those two images that our eyes see. And two ears give us sound localization, that we hear a sound here and we can work out where it is because the time of arrival and relative amplitude of each of those signals. So let's go through some examples in the robotics sphere of each of these types of sensor fusion. So what if a rangefinder gets blocked or becomes faulty or falls off our robot or something like that? Our robot will get all sorts of strange sort of data. So we could use multiple ones. Now they won't be quite the same position because it's physically impossible to put three sensors in exactly the same spot. So they'll give us a slightly different view. But they won't necessarily fail the same way, so that's some assurance against failure. So here we have three different rangefinders, and they're essentially voting on the range that they're seeing. So we might have three rangefinders stacked on top of each other, and they're telling us how far away an object is. We could have some sort of a voting mechanism, which is typically very commonly used within our redundancy, and we take the most common value or the most repeated value or an average of them as our expected output. Then we have complementary sensor fusion. So sensor fusion of different types. And I mentioned this one earlier. If we have infrared rangefinders, they have a limited range and don't work when we don't have reflection, but a very narrow beam width. We could couple that with ultrasonic that can reflect, that won't reflect back to us. They'll deflect at the wrong angle, but they have a very wide beam width. And so we could take the best of both worlds and develop a system where we have maybe some generalized rules for using these. For example, if the sonar data is greater than the maximum infrared range, then we ignore the infrared range because we know we're not getting something from the infrared light. If our sonar data is greater than the maximum value, then it's not the real distance. The real distance is actually greater than that again because it's timed out. And if the sonar data is less than 10 feet and the infrared data changes from detection to no detection very rapidly, it's likely that we've got some sort of depth discontinuity. We've got a pole there. So here's another area where we'd use complementary fusion. Multimodal image registration. And the basic idea is we take a an image with one type of a camera, just a visual camera, and another image with another type of camera, like a thermal camera. And we can register those images together to give us a multimodal image that tells us information about it. And we can use this when we're trying to troubleshoot things and look for a hotspot on a printed circuit board, for example, and work out which component's failing. I've done that a number of times. Very useful for looking at shorts in tracks and things like that. Or looking at motor wear and where the heat's being generated needs to be dissipated within our motor. Active and passive cooling systems as well within computer systems. Very useful using thermal imaging. But here we've got a visual image from a camera and a thermal image and combining them together. So two types of images giving this complementary sensor fusion. Another, and probably the most clear version of cooperative sensor fusion, is in stereo vision, where we have two sensors, each with a slightly different view. We've got some videos later on that explain all the ins and outs of stereo vision, but basically we've got these two different views, and based on the disparity of objects where we see them from one view to the other view, we can match those objects and then work out the distance from the cameras to those actual objects within the scene. Something that is quite often used in sensor fusion is some filtering. And here's another example of where we'd use it when we're combining data from different types of sensors. Complementary filters, frequency domain filters, essentially filtering out certain frequencies of data or allowing them to pass through. And sometimes there are different measurement sources with different frequency components of noise. For example, one might have high frequency noise and one might have low frequency noise. Essentially, we typically want to filter out the noisy bits but keep the good bits, and that way we reduce our noise and increase our signal to noise ratio. So the complementary filter is a filter that can be used in this particular area. So here's an example, assuming we have one signal with a high frequency noise and a second signal that happens to exhibit a low frequency noise. If we could filter out the high frequency noise from one and filter out the low frequency noise from the other and join them together in some sort of a summation way, we could have a reconstructed signal where we've removed both high and low frequency noise and got a better signal than either of those other ones. So one common example of how this is done is in creating inertial motion units with a gyroscope and accelerometer. For example, when we're controlling something like a Segway. We're really interested in finding the angular position of the object. For example, is it upright or is it a tilt of 10 degrees or whatever it may be. Now there's a few different ways we can do this. One of them is we can use our gyroscope, and if we integrate our angular velocity of our gyroscope over time, it will give us our angle. We can also use our accelerometer to determine the position of gravity and work out this gravity vector over time. The thing is, our gyroscope, as it integrates over time, has a tendency to drift. So it won't return back to its zero position. And if we put it on the bench and don't touch it, it will drift fairly slowly over a period of typically tens of seconds to minutes. So it's reliable for the short term though, but not reliable for the long term. So we can apply a high pass filter here, where we want the high frequency signal, but the low frequency signal where we have this long-term drift we want to minimize. We also have a similar problem with accelerometers, but the other way around. The gravity vector isn't the only force the accelerometer sees. Every little movement, every little bump, motor vibration from the drive system, this will be picked up by the accelerometer. And here we need to filter out the high frequency noise and have a low pass filter on our accelerometer. So it's reliable for the long term, but that high frequency noise we want to remove. So we get something a little like this. We get our accelerometer data and low pass filter it. We get our gyroscope data. Once we've integrated to get our angle, we high pass filter it and we get our output. And here's the sort of output that we expect from it. So a complementary filter, we have in green the accelerometer data, and we see it's quite noisy. Lots of high frequency noise there. And in blue we've got our gyroscope data. And we see particularly at the end there where that drifts off, it hasn't returned back to its zero value. But then when we complementary filter it, we get the red signal, which removes that long-term drift from the gyroscope and removes the high frequency noise from our accelerometer. Now the code for this isn't very complex. Here's a very basic implementation of it. And essentially what we're doing is we're multiplying our gyroscope value by a weight and multiplying our accelerometer data by a weight. And this, although it's not strictly complementary filtering, it approximates the sort of results that we get from complementary filtering to give us a decent result. Our other lines of code there are allowing us to calculate the angle due to the gyroscope and angle due to the accelerometer there. And we do this at regular time intervals. Another type of filtering that we're not going to cover, but we should introduce, is Kalman filtering. And we've mentioned complementary filtering as a very simple and computationally inexpensive approach to filtering. It was only a few lines of code as we had there. Now, Kalman filtering is another technique. It's quite computationally expensive. It's conceptually a lot more difficult to understand, but provides often much better results. We need to weigh up the complexity and the computational power that we have available to us as to which sort of technique that we're dealing with. If we're dealing with a mobile robot that's in a limited processing environment, we might go with a complementary, but if we can have MATLAB and other things available to us, and people typically use toolboxes and things like that to implement these sort of things, our Kalman filtering typically will give us a much cleaner option.